All right, welcome AMC. I know some of you folks have been having some trouble with this assignment, the synchronous assignment for this week. So I am going to help you out with problems on that. This is number 10 right here, and I'm not going to read it. You can do that. And what I suggest is that you pause your video and you write down all the important pieces of information from this question, and then come back and see what important pieces of information I wrote down. So go ahead and do that now, please. All right, let's have a look at what I thought was important here. So here are the pieces that I see as important, and we are going to write equations using these pieces of information. The first equations, though, that we're going to write, or I should say inequalities, not equations, the first inequalities we're going to write are kind of the most basic thing here. We are not considering reducing the salaries of the secretaries nor the faculty. So our x is going to be greater than or equal to y, and also or greater than or equal to 0, excuse me, and our y is going to be greater than or equal to 0. So that's saying that the percentage increase for salaries cannot go down, can't be less than 0. It's either going to go up or stay the same. And that's going to be the same for faculty members. Now, because they want to spend at most $5,000 towards raises, we can think of these these eight secretaries who right now receive $28,000 as their starting pay. If we're going to give them a percentage increase, that will be the X. So this is if you multiplied that, that would be the amount that they're going to increase the salaries by. So if you multiply the amount that they're going to increase the secretary's starting salary by 8, that will be the amount that they're going to increase salary secretaries for all 8 secretaries. And now we can think of the same thing for the 7 faculty members. They have a starting salary of 40,000, and we're going to multiply that 40,000 by the percent increase, and this will give the amount of money that we are increasing the faculty members' salaries by. And we know that when we add up the amount that we're increasing those 7 faculty members and add it to the amount that we're increasing those 8 secretaries' salaries by, we know that that total must be less than or equal to $5,000 according to this right here, at most $5,000. The other thing that we need to remember is it's the equation for the total expenditures. So the total expenditures, let's call it E, will equal 8 times 28,000 x plus 7 times, and this is just the total expenditures that they're considering increasing. So we're minimizing this equation. All right, so I'm going to take those equations, and this one right here is one we're going to need on the next slide. So I'm going to take it over. And here is what you see when you first graph those inequalities. I'm using the Desmos calculator here. And it appears as if the inequalities all intersect here at 0, 0. However, if we zoom in, we see that that is not the case. And the reason why we're so close to 0, 0 is because we're talking about percents. Remember that 0.01 here, this is a 1% salary increase for secretaries. This is a 2% salary increase for secretaries. This is a 1.5% salary increase for faculty members. So we have a few points to look at here, and we can rule out, well, here's 0, 0. We're not sure exactly what these 2 points are. We would have to uh, find those exact values and plug them into our equation. And remember our equation, our equation that we're talking about here that we need to uh, minimize is this right here. So we have those 3 points. But if we think about what is going to minimize this equation, our 0, 0 is what will minimize the equation. So this is saying, listen, if you want to minimize expenditures, then just don't give anyone a raise. You don't give out raises and you minimize expenditures. And unfortunately, that is the way things go sometimes. So the answer here is that there is a 0% salary increase for secretaries and a 0% salary increase for faculty members if you want to minimize expenditures. And I'm going to go back and I'm going to show you in the question what we might have noticed and not had to do any work on this problem. And that is right here. They want to minimize its total expenditures. If we had seen that, we would have just said, okay, well then 0, 0 is your answer. But we didn't, and there we go. 0, 0. I'm sorry I didn't give you any warning that you should have paused the video and gone and graphed those equations and the inequality rather on Desmos. I'll give you that warning next time. I'm sorry about that. All right, on the next one, here is the question. Pause the video right now and come back after you have written out all of the most important pieces of information. All right, here are the most important pieces of information. Actually, my suggestion is that you pause the video now and you try to write down the equations for these most important pieces of information. All right, now we'll go over writing the equations for these. So I see right away that I've got a situation where we have this 30 minutes to make a pair of earrings. Let me highlight that with a yellow. 30 minutes to make a pair of earrings, 1 hour to make a necklace, and 10 hours a week to make jewelry. So what we can think of is that she has 30 times X. So however many earrings she decides to make in a week, you have to multiply it by 30, and that will give you the amount of minutes it takes to make pairs of earrings. Add to that, now be careful here, 1 hour and 30 minutes. These are in different units. So we want to say plus 60y. So that's the amount of time that she's going to spend making necklaces in a given week. And that has to be less than or equal to, at most, 10 hours a week. So less than or equal to 600. So that's one of our equations right there. The next one that we can look at is only enough material to make 15 jewelry items per week. So that means that the number of pairs of earrings plus the number of necklaces has to be less than or equal to 15. All right. Now the equation that we are looking to minimize or maximize is going to be about profits. So she makes $15 profit on a pair of earrings, $20 profit on a necklace, and we want to maximize profit. So here, profit equals 15 times the number of earrings that she makes, plus 20 times the number of necklaces that she makes. And as you look at this, you might think, well, then she should just make necklaces. But once we graph the inequalities, it's obvious, it becomes a little more complicated. The other thing that we want to make sure that we remember is that she can't make negative earrings or negative necklaces. So x is greater than or equal to 0, and y is greater than or equal to 0. So now what I recommend doing is going and on the Desmos calculator, graph these inequalities and see if you can figure out how to maximize that profit given the graphs. Here's what I got when I graphed those inequalities. And we can put the points of intersection in here. So right there we have 10, 5. We only need to look at the corners of our solution set. Here's 15, 0. Here's 0, 10. And here is 0, 0. So what I didn't say, but have made clear, I hope, is that this right here is the solution set. And so everything inside here, these are all possible numbers of earrings, X, pairs of earrings, X, and necklaces, Y, that she could make. But this one right here, we can throw that out. We know that's not going to maximize profits. Not making any pairs of earrings and not making any necklaces will not make her any money as well. So the equation that we needed to bring over to maximize is this one right here. Let's bring that over. And so we're going to plug in our x and y points into that equation. So we have profit is equal to 15 times, and I'm going to start with the point 0, 10. So 0 plus 20 times 10, and that will turn out to be, whoa, 20 times 10, not times 20. So that would turn out to be 200. So in that case, profit equals 200. And in the next one, we'll do 10, 5. So profit is equal to 15 times 10 plus 20 times 5. And in that one, 15 times 10 is 150. 20 times 5 is 100. So it's 250. And I cut it a little closer and scoot that one over. Here we have a profit is equal to 15 times 15 plus 20 times, I still need a little bit more room here, sorry about this, 20 times 0. So 15 times 15 is 225 plus 0. So our solution then is going to be the point 10, 5, which results in a profit of $250 per week. All right. The last problem here about bountiful boats. You read over it and see if you can write down all the most useful pieces of information. So pause your video and do that. All right, let's have a look at those most important pieces of information. and start to, you have a look at those, and I suggest, again, pausing the video and trying to create inequalities that you'll need to graph and the equation that you'll need to maximize for costs here, or minimize costs, excuse me. So pause the video. All right, so we're going to start off by noticing that we're talking about the number of days per year that Michigan factory should run is X, and the number of days per year that the Wisconsin factory should run is Y. And I see that they can run at most 240 days per year, right there. And it's important to also note that a factory cannot be open for less than 0 days or a negative number of days. So the first inequality that we can write is that 0 is less than or equal to X, the number of days that Michigan should be open, which must be less than or equal to 240, and 0 is less than or equal to Y, which is less than or equal to 240. So both of the factories have to be open between 0 and 240 days. Now, the next part that we're going to focus on is that we need to produce at least 5,000 cabin cruisers. Michigan makes 20 cabin cruisers. Wisconsin makes 10 cabin cruisers. So if we think about writing an equation, an inequality for that, if we take the number that Michigan makes per day, 20, and multiply that by the number of days that Michigan is open, and add to that the number that Wisconsin makes per day, 10, times the number of days that Wisconsin is open, that number needs to be greater than or equal to 5,000. Similar to that, if we think about that they need to make at least 12,000 pontoons per year, Michigan makes 40 per day, Wisconsin makes 30 per day. So 40 times X, that's 40 pontoons per day, X days at Michigan, plus 30 pontoons per day times the number of days that Wisconsin is open. That number must be greater than or equal to 12,000. Now, lastly, we have they want to produce at most 30,000 jet skis. And Michigan makes 60 jet skis a day. Wisconsin makes 50 jet skis a day. So using that information, 60 times X plus 50 times Y can be at most 30,000, so less than or equal to 30,000. So those are the inequalities that we're going to be using. And we want to minimize costs. So costs are equal to, Michigan is open per day. It costs 960,000 to run. So 960,000 times X. So that's how much it will cost to run Michigan X days, plus 750,000 times Y. That's how much it will cost to run Wisconsin Y days. And that is the total cost. And what we're trying to do is minimize this. So we're going to need to take this over. And I would recommend pausing and graphing those inequalities on Desmos graphing calculator. All right. So here is the equation that we're going to try to minimize. And it's kind of hard to see, but our region is in here. And up here, there's a point of intersection that I cut off. I'm sorry about doing that. It turns out we don't need it because, oh, we didn't cut it off. It's right here, sorry, because x has to be greater than 0. So this is our region right there. Sometimes hard to tell. And that is one of the reasons why it might be good to do the opposite shading, especially with this many inequalities. So if we're trying to uh, minimize costs, we are going to need to plug in the points from that that graph there. So you want to make sure that you find those points. So you can just click on them using the Desmos and figure out what they are. So I'd pause the video now and do that, please. Uh-oh, I hope you went and graphed that and said, wait, Mr. White Wolf, something's going on, because something was going on. These points are not part of the solution set. If we zoom in here, we can see that these points are what the solution set. So it's a good thing that I took that time to graph those. I went and graphed them myself just now. And so we have this point, which is 240, 240. So both plants being open 240 days a year. This one's 240, 80. This one over here is 130, 240. And this last one is, whoops, 150, 200. Now, because we're trying to minimize costs, we can rule out certain situations. So if we think of these 2 points, this one is going to cost more. So if we're minimizing costs, then we can rule it out. We could have also seen the same way here. So we really have 3 that we need to check. So our costs, then, here, costs are going to equal 960,000 times, and I'm going to start with the 130, 240, 130 plus 750,000, 240, and I'm going to do that on my calculator real quick, and I get that the cost is equal to 304. I just messed that up. No, it's just 304,800,000. It's a lot. All right, so that is one of those. So let me see what's going to be the best way to do this. I think I'm going to copy it and I'm going to shrink it down, put it up. I'll just put it right here. Okay. The next one, cost is going to equal 960,000 times, I'll do the 150, 200. So X is 150 plus 750,000 times 200. And that is going to equal, it's going to equal 294 million. All right, so let's save that, shrink it down. And lastly, we'll have the cost is equal to 960 million or 960,000 times, and this is the 240/80 problem, plus 750,000 times 80. And that's going to come out to be 290,400,000. So if the company wants to minimize their costs, then it appears to me that this is going to be the one to do it, where the, let's see, which plant? The Michigan factory is open 240 days, and the Wisconsin factory is open 80 days. So I hope that this video helps. These are tough problems, there's no doubt about it. And if you need some more assistance, come see me during the asynchronous period.